Good morning and good afternoon, everyone. It's afternoon for me in Florida, where I am. And welcome to our presentation today. I'm Marilyn Barger. I'm the Executive Director and the Principal Investigator of NSF Advanced Technological Education Center in Florida that's focused on manufacturing across the state. So we work with all of the two-year programs in the state that support manufacturing. We're going to talk a little bit about that degree program in the context of this talk. So first of all, just a little bit about who we think we are and what we want to do is be the go-to place for manufacturing education in the state. So this is a kind of a big vision. And for us, it involves all of the high schools and community college programs across Florida that support manufacturing. Means we interact with a lot of different people, a lot of different organizations, a lot of different schools to do a variety of different things, all to support the manufacturing workforce. And in the NSF Advanced Technological Education Program, we kind of bucket our work in three big areas. So professional development is one of those. This supports program growth and strengthens the programs by providing information to faculty and teachers about the newest technologies, not just that they're used in manufacturing, but also that are used in teaching. So hybrid courses, project-based learning, as well as new technologies that might find their way to factory floors. Also, to strengthen programs, we do a lot of work with the curriculum. In Florida, that work is done in partnership with the Florida Department of Education. They have a serious career and technical education division that oversees the programs and makes sure that they're aligned to industry needs. So we work with those folks in Tallahassee to make sure that the manufacturing programs meet industry needs across the state. Just a note on that, we have a legislative mandate to review those frameworks, as we call them, for these programs every 3 years across the state, and the Florida Department of Education is bound to submit those reviews and publish updates on a every 3-year cycle. And the last bucket that we do, that we work in, again, to strengthen the programs is outreach and recruitment. Although we have good and strong enrollment in our programs, we are a little weak in a couple areas. One is in the high school to community college program, recruiting young students into our 2-year technical program, but also recruiting women. So we do spend some time and effort doing outreach and student kind of events to expose them to the career paths and educational paths for manufacturing. So within that context of that, additive manufacturing is part of our curriculum. This is what our degree program looks like in Florida. Generally, it's divided into 3 little segments. Gen Ed, pretty straightforward. We have defined, in partnership with the colleges around the state, we defined what we call an engineering technology core. Those are courses you can see on the red stripe, on the middle stripe in your screen. That are fundamental to going on in these 11 different specialized tracks that you can see in the last stripe, which is blue at the bottom of the screen. So within that, schools can choose to offer as many of these different tracks as they want, depending on their industry and their area and the needs that those folks have for workers, for their workforce. But specifically of interest to this particular group online are the 2 specializations that are circled here: digital manufacturing and digital design and modeling. So remember, these are 2-year programs. The second year of the program is like 100% hands-on stuff. It may not happen that way chronologically for a lot of students, but in theory, they've taken the engineering technology core courses first and then move into one of these specializations. So for the world of additive manufacturing in those 2 tracks, I've put a typical, although not exclusive, set of course titles, at least, to give them a name, of the courses that make up that, where additive manufacturing would be part of many of the courses that you would see on a screen. So digital design and modeling is much more focused on 3D printing, working with models, and working with the equipment involved with reverse engineering, modeling, and 3D printing or additive manufacturing strategies. The digital manufacturing courses is kind of a combination of, as you can see, both the additive and CNC, which is some people will now call subtractive programming. So giving them a lot of focus on the modeling piece and design part, but having a reasonably strong focus on both additive and subtractive within the program. So this is a variation of needs in different parts of the state. The colleges that offer digital manufacturing are up in the Florida Panhandle. I'm going to show you that in a moment. And the digital design and modeling program are found down in the colleges that offer that are further down in the state. In the Panhandle, we have a lot of fabrication related to the military. There's several large Air Force facilities in the Panhandle that are supported by the colleges there. So before we look at the schools, this is what the overall program looks like in a little maze. Our two-year programs are all about opportunities for on-ramps and off-ramps. We do a lot of our on-ramping and off-ramping through certifications, industry certifications of various kinds. And our key certification for getting into our two-year degree program is the MSSC Certified Production Technician. I'm not going to talk too much about that, but it's a certification they can get credit for and apply it to those core courses in the engineering technology program. And on the right, you'll see all those 11 specializations in the second year part where students would take the digital design and modeling or digital manufacturing, as well as some other options there. All right, so just to remind everybody what Florida looks like, it's a big state in a lot of ways. And it's a very long way from Pensacola over here in the far west down to Florida Keys College, Florida Keys Community College, down in the Florida, down in the islands in the Florida Keys. So this is our network of colleges, and the schools that actually offer a focus on additive manufacturing are highlighted here, so I won't read them. You can see where they are, different parts of the state. It's not that there's not additive manufacturing going on at the other schools, it's just they don't have that particular track. Each of the programs in the state offers AutoCAD, Inventor, and/or SolidWorks in a number of courses. And all of those colleges on the map that are involved in the engineering technology degree have at least, I would say probably all of them have 2 3D printers that they work with in the students in those courses. So they do some as part of their technical program, but these particular colleges actually have a focused degree program for that. Okay, so what I'm really going to talk about, is a little background about what's happening in Florida, is the result of a workshop that we did, or a little bit about this workshop that we did about 2 years ago. It was hosted by St. Petersburg College and the faculty there. So if you remember back on one slide, St. Pete College was one of those that offered the digital design and modeling. And they have quite a nice facility there in St. Petersburg. Sorry, it's on the Clearwater campus. So the focus of this this particular 3-day workshop that we did in partnership with the Digital Fabrication Learning Community and the Fab Lab Network was we're struggling with to get some answers for the question a lot of educators have about where do we use how do we integrate the fab labs and all of the capabilities that they have into our academic programs? How do we utilize the facilities best? How do we align them with some of the curriculum pieces that we're required to teach and that students need to learn as they go through their technical programs? So we had went through this process of developing and designing this particular piece that you see here, the crank power transfer module, and went through the 4 stages you see on the slide. So we did some reverse engineering, then modeling, additive and subtractive manufacturing, that had a option to do some machining or 3D printing during the workshop, and then some tests in metrology to make sure that, and form and fit to make sure that the piece worked. So the idea was to do the whole kind of design manufacturing process, as well as spend some time on the particular processes and identify as they went through where they were learning something that they actually taught and would teach in a classroom in one of their courses in a program. So the participants were from all over the country, and they had their own programs of sort. So we've got a variety of output that we're going to look at in a little while, but towards the end of this presentation. But that was the idea, to go through the manufacturing process, do some do processes and use equipment that we would find in a fab lab, which included a lot of additive, and then see how it really aligned to the programs. So this is just a slide filler to show you that some of the documents that we produced in order to get there, we designed the little crank power crank transfer assembly, and got a little bill of materials there. And now I'd like to kind of run through what we did parts of during the workshop. This is to see the assembly that we worked on, in the planetary gear array at the bottom that the black assembly is sitting in was the test. So we needed to reproduce this crank to run this gear system.
We're going to do the crank power transfer module project. And again, the purpose of this workshop is to become exposed to the manufacturing processes modules through project-based learning. We will cover the basic steps of rapid prototyping while turning our project into a finished product. The manufacturing process begins with reverse engineering of an assembly from which the design is made. Manufacturing processes can include additive, subtractive manufacturing, machining, and reshaping of material. The manufacturing process also includes test and check for quality assurance both during and after the manufacturing process. To ensure success, it is necessary to plan the product's process prior to manufacturing or making modifications to the product. The procedures will be Module 1, reverse engineering and measurement; Module 2, part modeling using SolidWorks, a 3D parametric solid modeling software; Module 3, which is creating the parts in the 3D printing or CNC machining. And then the final module will be assembly and form fitting of the parts into the assembly. The first thing we will do is measure and check the size and shape of the parts we're going to reverse engineer and measure. The length and the diameter of the pin. We're going to note and document all sizes so we will be able to modify and model these parts within SolidWorks. Once we model our parts and we determine our sizes and shapes, we will model those in SolidWorks. Again, the spider gear, and then also our female and male yokes for this project. Again, we will reverse engineer in many different ways. Once we're done reverse engineering and modeling our parts within SolidWorks, we will take those to the 3D printer and we will create these parts with the 3D printer. Once we get our parts created, then we'll go in and assemble them for our final project, which is the crank power transfer, which the purpose of this is to turn the planetary gear down below. So once we're done reverse engineering and modeling our parts in SolidWorks and 3D printing them, we will bring them together and assemble them. Now the first parts that we will assemble will be our spider gear and our male and female yokes with our pins. Again, this is a picture of our assembled product and our modules. Our goal at the end is to assemble our product and then go ahead and finish documenting the project in SolidWorks with a assembled and a exploded view with balloons and a BOM, bill of material. This is the male yoke. Alright, these are our short pins. This is our spider. We've got our long pin. We have a female yoke. We have our crank arm assembly. We have our crankshaft and our bracket, which supports all our parts here within the assembly. The first thing we will do is we will assemble the male yoke with the spider with the short pins. And next we will insert that into the bracket right here, and then turn on angle, and then come in with the female yoke. And then insert the long pin all the way through. And again, we have rotation. And again, both the female and male yoke is attached to the spider gear. And again, we can rotate and then place in position and alignment with the bracket hole. All right, for our supporting shaft that goes into our planetary gear. Now that we have our female male yoke, all right, inserted with our spider gear, we'll come in with our crankshaft. And again, with our crank arm and knob. All right, we have it assembled, and it seems to fit good. and it seems to rotate without any problems. Now that I have the power crank transferred assembled and it seems to turn without any hesitation or drag, now I will try to insert it into the planetary gear to see if it works. So again, I'm going to remove the original power crank transfer that we reversed engineered, and insert the drive shaft and insert it into the planetary gear, and then see if it works and turns the planetary gear. And it seems to turn good, and it seems to power the planetary gear around in its circle of path. And again, all the parts seem to fit. All right, and again, we have a good project. Everything assembles, and now the next thing we'll do is do simple modification if we have to, and to finish this project up. Again, if you take a look, here is the exploded view with all our parts. Here is an assembled view with the BOM, bill of materials. All right, and then again, this is our goal right here, is to assemble, form, and fit. And again, we're done with our project. Thank you very much.
So the idea, of course, was to have this build experience, which we already talked about. I think maybe I can move right to the next slide with a couple of the outcomes that we had for the academic point of view. So we had the participants, there were about 20 to 24 faculty there, and we asked them what courses the processes that they used would align with, where they could use that part of this exercise for teaching in their particular classrooms. And you can see the CAD, the drafting, and CAD being including SolidWorks, 3D modeling, of course, came up in most of these the discrete activities that we asked them to define, and a couple of other courses, particularly the intro to engineering or intro to technology, and also capstone courses came up, that same kind of project-based learning course that many programs might have as part of the curriculum, required curriculum. And very specifically, the metrology aspects, the measurement using some variety of tools, although in the video you only saw him measuring with calipers. They have some optical comparators that were used, and CMMs that were also used in the processes during the workshop. So all of that technology may be part of a metrology course, and introducing them in those courses and doing part of the project or using the project as a particular piece for a capstone course or an intro course of some kind were all possibilities that came up. So we know that a couple of the colleges for sure implemented the project and tried some alignment with their different programs. Some more successful than others. We didn't hear back from all of the participants, of course, but quite a few thought that it was good opportunity to use fab labs that they had in their facilities or maker spaces, whatever, to integrate their courses. It did come up that there's a lot of logistic issues with that, depending on the openness of the facility, if it's open to the public, and scheduling, those kinds of things, if there's a fair number of students working, and that all of that was a kind of individual institutional issue that they would just have to deal with. And one thing that's not on this list, I guess, was also the supply. So if materials were used, that needed to be considered and figured out how those would be paid for. So that's it. That's all I have. I'm sorry about all the technical difficulty. And if you have any questions, I'm happy to try to answer them. Again, you can find those files on the website down at the bottom of the slide, www.flate.pbwiki.com, and look for the advanced manufacturing or additive manufacturing